The concept of a habitable zone is central to the study of astrobiology and planetary science. It refers to the region around a star where conditions might allow liquid water to exist on a planet's surface, a critical criterion for life as we know it. In the solar system, the habitable zone encompasses a dynamic interplay of planetary characteristics, solar radiation, and other environmental factors. This description explores the concept of the habitable zone, its relevance to the solar system, and its implications for the search for extraterrestrial life. The habitable zone, often called the Goldilocks zone, is neither too hot nor too cold for liquid water to exist. It is determined primarily by the luminosity of the star and the distance of a planet from it. For the Sun, this region roughly spans from 0.95 to 1.37 astronomical units, AU, with Earth located conveniently within it. However, the HZ is not a fixed concept. It depends on a variety of planetary and stellar parameters. A brighter star extends the habitable zone farther out, while a dimmer star shrinks it. The Sun, being a G-type main sequence star, offers a moderate habitable zone compared to more luminous O or B stars and dimmer M dwarfs. A planet's atmosphere can significantly affect its surface temperature. Greenhouse gases, such as carbon dioxide and methane, can trap heat, potentially expanding the habitable zone outward. The reflectivity of a planet's surface affects how much solar energy it absorbs. A high albedo, such as ice-covered planets, reduces surface temperature, potentially shifting the planet out of the HZ. Internal heat sources, such as radioactive decay or tidal forces from nearby moons or planets, can provide additional warmth, allowing for liquid water even outside the traditional habitable zone. In our solar system, Earth is the prime example of a planet within the habitable zone. However, other celestial bodies exhibit characteristics that suggest they might harbor liquid water under certain conditions. Earth is often considered the benchmark for habitability. It lies at an optimal distance from the Sun, allowing for stable temperatures and liquid water. Its atmosphere, composed of nitrogen, oxygen, and trace greenhouse gases, provides a stable climate and protects life from harmful solar radiation. Mars, located at the outer edge of the Sun's habitable zone, is often seen as a potential candidate for past or present habitability. Evidence from rover missions suggests that liquid water once flowed on its surface, creating river valleys and lake beds. Today, water exists primarily as ice, but subsurface reservoirs of liquid water may still persist, fueled by geothermal heat. Venus, despite its proximity to the Sun, lies within the theoretical habitable zone. However, its thick atmosphere, composed predominantly of carbon dioxide, creates an extreme greenhouse effect, raising surface temperatures to a scorching 475 degrees Celsius. This makes Venus inhospitable to life as we know it, highlighting the importance of atmospheric composition in determining habitability. While the classical habitable zone focuses on surface liquid water, other regions in the solar system might support life under different conditions. These environments challenge traditional notions of habitability. Europa, a moon of Jupiter, is a prime candidate for extraterrestrial life. Despite being far outside the Sun's habitable zone, Europa harbors a subsurface ocean beneath its icy crust. Tidal heating, caused by gravitational interactions with Jupiter, keeps this ocean in a liquid state, providing a potential habitat for microbial life. Saturn's moon Enceladus also hosts a subsurface ocean, evidenced by plumes of water vapor erupting from its surface. These geysers contain organic compounds, suggesting that Enceladus may offer the necessary ingredients for life. Titan, another moon of Saturn, possesses a thick atmosphere and lakes of liquid methane and ethane. While these conditions differ significantly from Earth's, Titan's complex organic chemistry makes it an intriguing target for astrobiology. Planets and moons with significant geothermal or tidal heating, such as Europa and Enceladus, demonstrate that habitability is not solely dependent on solar radiation. These energy sources can create localized habitable environments even in the cold outer regions of the solar system. The concept of habitability is inherently complex and context-dependent. Several challenges complicate its definition and application. The habitable zone evolves over time as a star's luminosity changes. For example, the Sun was less luminous in its early history, meaning Earth's habitability evolved alongside its star. Life on Earth thrives in extreme environments, such as deep-sea hydrothermal vents and acidic hot springs. These examples suggest that habitability may extend beyond traditional criteria. Identifying signs of life, or biosignatures, on other planets is a significant challenge. Atmospheric gases like oxygen and methane can indicate biological activity, but they can also arise from abiotic processes. The study of habitable zones has profound implications for the search for extraterrestrial life. Missions like the Kepler Space Telescope and the James Webb Space Telescope aim to identify exoplanets within habitable zones of their parent stars. Meanwhile, planetary exploration missions focus on bodies within our solar system that might harbor life. Scheduled for launch in the 2020s, the Europa Clipper mission will study Europa's subsurface ocean and its potential for habitability. The Dragonfly mission will explore Titan's surface, analyzing its chemistry and searching for signs of life. Ongoing efforts to bring samples from Mars back to Earth aim to uncover evidence of past microbial life. The discovery of thousands of exoplanets has expanded the scope of habitable zone studies. Researchers now explore not only the potential for Earth-like planets, but also super-Earths and mini-Neptunes that could host life under different conditions. The habitable zone is a cornerstone of astrobiology, offering a framework for understanding where life might exist within the solar system and beyond. While Earth remains the only known habitable planet, the discovery of subsurface oceans on moons like Europa and Enceladus has expanded our perspective on where life might thrive. Future explorations, both within our solar system and among distant exoplanets, will continue to refine our understanding of habitability and the potential for life beyond Earth. By studying the diverse environments of the solar system, we take crucial steps toward answering one of humanity's most profound questions. Are we alone in the universe?